Okay, so scientific notation, also known as standard form. So we're just going to put down, it won't be too long a note, but we're going to say when we have to write extremely large or extremely small numbers, it is easier to write them in standard or scientific notation or standard form. Which?
The first one.
We.
Well, after that.
When, sorry, it should say when we.
Okay.
When we have to write extremely large or extremely small numbers, it is easier to write them in scientific notation. So for example, the number, let's have a look at one of the ones from yesterday. 4150000. Written in standard form. So I'm going to use standard form or scientific notation interchangeably. It's the same thing though. It's written as Alright, so in standard form it's written as 4.15 multiplied by 10 to the power of 7. Okay, and we'll explain how we go from writing it out in full to writing it out in standard form, or standard notation, I should say. Okay, everybody got it down? Missing Hannah, and we're missing Marina. Yeah, thank you.
She's right there.
Cheers. Thank you. Okay. So where is this useful? Everybody got it down so far? All right. So if I go to this, so I'll show you this little scale of the universe. So this is where scientific notation really comes in handy. Sorry about turning the sound off. Some of you may have seen this before. But on the bottom here, we've got 10 to the power of 0. What's anything to the power of 0?
1.
1. Okay, so that represents 1 meter. Okay, so this little circle here represents 1 meter. Okay, so a human is slightly bigger than 1 meter, well, about 1.5 meters. And what we're going to do is we're going to start zooming out. Okay, so we can see the size of things. And as we notice, I go, sorry, a bit slower. Very sensitive. Okay, if we notice the little 10, it's actually going up. 10 to the 0.2, 10 to the 0.3, 10 to the 0.4, and if I go to, if I can try and stop. Okay, 10 to the 1. What's 10 to the 1? Javian? 10. Okay, so that means it's 10 meters. These things are roughly about 10 meters long. Okay, so we got 10 meters for the side of a house. A Siguro cactus is about 10 meters tall. All right, so it's easy enough to write 10, okay, than it is for 10 to the 1. But as we keep going out and the numbers keep getting bigger, we can see that if I go to 10 squared, what's 10 squared? Put your hands up. 10 squared. Put your hands up, please. High. Isa? Yep, which is? Yep, but it is actually equal to 100, okay? So we got the redwood tree, which is 100 meters, okay? Boeing 747, which is roughly about 100 meters, and the International Space Station. And again, the number 100, yeah, it's not a big deal. We can easily write 100. It's not any quicker to write 10 squared, but if we keep going, so we get, so that's 1,000 meters. We've got Central Park there. We'll keep going out. 10 to the 4. Now, what's 10 to the power of 4? Equal to. Diana? 10,000? Yep, absolutely. Okay, so a 1 with 4 zeros. So that's 10,000 meters. So we've got Mount Everest, the depth of the Marina Trench. What's the Marina Trench, Hans? Anyone? Yes, Josh? Yep, the deepest point in the ocean. Do you know whereabouts it is? Actually, I thought it was the Atlantic, but it might be the Pacific. Is it the Pacific? Yeah. Cool. So yeah, it's the deepest point of the ocean. All right, and if we keep going, got Rhode Island. I think these might be planets, not planets, moons, different moons. So now we've got 10 to the power of 5, which is a 1 and 5 zeros, so that's 100,000 meters. Keep going. We've got the Grand Canyon, California. Okay, so we've got 1,000 meters, sorry, 1,000,000 meters. So we've got the length of California is also the same as the length of Italy. And again, let's keep going. So we're getting out to the planets.
Minecraft.
Yeah. Minecraft world is roughly about 10 to the power of 7.7. Okay, so it's pretty big. Yep.
What is infinite? Just keep it doing this.
No, it'll be a certain fixed amount of space. Okay.
Not really important.
Okay, if I go to 10 to the power of 9, let's see where we are. All right, so when we start getting up to these kind of numbers, so 10 to the power of 9. So 10 to the power of 9 is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Why would it be easier to start using exponents like 10 to the power of 9 rather than using something like that? Yep, Ian? Because it's what you do. It's easier to write, yep. It's easier, it's quicker. What else? What about if you had to like do multiplication and addition with this? It takes up too much space. You're more likely to make mistakes with a long number like this, okay? Easier to deal with something like 10 to the power of 9, okay? A quintillion is 18 zeros. Okay, let's see if we can get up to a quintillion. So, anyway, the sun is that many meters, 10 to the power of 9 meters. We keep going. Now, these are other different stars. 10 to the power of 10. All right, so there is 10 to the power of about 11. So that's the distance from the Earth to the sun. All right, so there's a terameter. A terameter is 10 to the power of 12, and again, we can start to see that you can easily make mistakes when you're dealing with large numbers like this. It is a lot easier to use the exponents. If we keep going. Distance from Voyager 1 to Earth. Who has heard of Voyager 1? Anyone? Yep. Put hands. Who can tell me about Voyager 1? Stephanie, can you use your hand up? You've heard of it? Do you know anything about it? You just heard of it? Okay. Aiden? Spaceship, yep. And go on, Rajan.
It's the farthest runaway.
Yeah, it's the well. It's obviously it's man-made. It was sent off, I think, in the 70s, and it's the object that is the furthest distance from Earth. Okay, and it keeps traveling further and further and further away from Earth. And what they did whenever they actually built it, they put a lot of things from Earth onto it. They put music, like old kind of style records. They put books in there. They filled it up with things from Earth, just in case that any other kind of life finds it. Then they'll be able to see, you know, what Earth has done and where Earth is, and they put kind of the solar system of where Earth is, so then they can be contacted, which is kind of cool. And then this picture, actually, you may have seen online. So this is called Pale Blue Dot. This is taken from Voyager 1, and although it just looks like a dark piece of paper, it's not a star, that's actually Earth. It's really small, yep. And that's like the furthest picture away from Earth ever, okay? But you can kind of pass that around if you want. It is still transmitting signals, yeah, but it's getting fainter and fainter, and it's taking longer and longer for them to send them back. But it's kind of cool. All right, so if we keep going, you can just pass it around, Javian.
It looks like Marina on a map.
Just keep passing. Yeah. All right, so we've got now. I think these nebulas are clusters of stars and things.
It's like a mass of stars sitting in them.
Okay, lots of different nebulas. We'll keep going.
They've been getting blind.
All right, so here we've got 10 to the power of 18. So a quintillion. Okay, so this is a quintillion meters. Here it is, and Yeah, and again, can I click on it? So this is also known as this nebula, and there you go, cluster of stars, I'm thinking. And you can see that, obviously, I would not want to be writing out all these numbers if I'm trying to do any kind of calculations, okay?
It could be fun.
Emily, can you stop? Okay. It's a lot easier just to deal with 10 to the power of 18, okay? And that's what these numbers are used for, okay? They are actually used, so they're very, very important. And we can keep going. I'm going to start going a bit quicker here. We keep going out.
Milky Way.
Where was the Milky Way? Oh, there we go. So the Milky Way about 10 to the power of 21 meters. Okay. So it's 10 to the power of 20. Okay, now this is starting to group galaxies and things together. There's 10 to the power of 24. And this is what physicists would look at, and they would deal with all this kind of things.
What is 24?
10 to the power of 24?
No, what is this 24?
Oh, I don't know. I don't know. But it's this number. Yeah, they actually know this. They would work this all out, yeah.
How do they see this? It's called drones.
Well, it would, all right, let me keep going. All right, so if we keep going out, then we've got the observable universe. So this is kind of pretty much what can be observed, which is 10 to the power of roughly about 26, 27, which is 1 with 26 or 27 zeros. So that's the estimated size of the universe, okay? 10 to the power of 27, so 1 with 27 zeros. So if we go back to the start,
you'll see it. Minecraft!
there you go, there's Minecraft, 10 to the 7. Uranus. Alright, so if we go back to the start. Alright, so that's 10 to the power 0. So, whilst scientific notation on our exponents is really useful for very, very large numbers, we also said it's useful for very, very small numbers. Can people stop coloring in and actually listen and pay attention? So, if I start going the other way, I'm going to have 10 to the negative numbers. So let's see if we can remember. If I go to 10 to the negative 1. Right, 10 to the negative 1. Who can remind me what 10 to the negative 1 means? Hands. Yeah, it's going to be decimal, but what does the negative part mean? Hands up. Yes, Taylor? Reciprocal, good. So it means 1 over 10 to the power of 1. Okay, and if I was to actually work this out in the calculator, what am I going to get?
10.
Yeah? 0.1. Okay, so 10 to the negative 1 is 0.1. If I had 10 to the negative 2, what's that going to be as a fraction first? Yep, yeah, it's going to be 1 over 100 because it's 1 over 10 squared. So it's 10 times 10. And then as a decimal, it's going to be so as a decimal.
Oh, 0.0.
Up. Go on as well.
0.00.
Careful. How many zeros is going to be?
0.3.
Like that?
No.
One more zero.
Yeah, it's 1.
Okay, it's going to be 0.01 because remember this is my hundredths column, okay? My tenths column. 1/10, 1/100th, okay? So we can keep going this way. So we got hummingbirds, a shrew, a quail egg, coffee bean, so that's 10 to the negative 2. So that's roughly the size of a coffee bean, 0.01 meters. We can keep going. We've got ants, dust mites, so 10 to the negative 3.6. So at this point, 10 to the negative 4, we've got the smallest thing visible to the naked eye. So the smallest kind of thing you would be able to see. That's 10 to the negative 4, which is going to be 1 over 10 to the power of 4, which is going to be, what's it going to be as a decimal? What's wrong with you? What's it? Yep. 0.0001. Okay, all right, good. So 0.000001 of a meter. Okay, that's the smallest thing visible. We can keep going then. Width of a silk fiber. We've got chromosomes. We've got wavelengths, viruses. Okay. I'm not sure. Okay, we got the HIV virus, hepatitis B. Okay, we've got strands of DNA, which is 10 to the power of negative 8, so very, very, very small. Yep, 10 to the power of negative 8. 1, 2, 3, 4, 5, 6. Okay. So again, I want you to realize that using these numbers, okay, is a lot easier than having to write out a whole pile of zeros. Say again?
Isn't it one more zero? Because it's supposed to be 7 zeros and then the 1. No,
yeah,
it's 8 zeros.
Sorry, it's 7 zeros.
Yeah, it's 7 zeros and then 1. Yeah.
6, 7.
Ah, it is. Because if you
See,
4,
it's easy to make mistakes when you're using them. All right, if we keep going, we're going to go a bit quicker because a lot of this stuff, we've got atoms, we've got gamma ray, wavelength, we've got a uranium nucleus.
How small uranium is? Vibranium.
Okay, so when we get down to this point, scientists and physicists have said that lengths shorter than this are not confirmed, so it's difficult to measure them. The weak force is one of the 4 fundamental forces of nature and is the weaker of the 2 nuclear forces. There you go. Okay, so we got quarks. And then I think at some point, yeah. So it keeps getting smaller. There's not much here to really look at because it's so small. But if we keep going, we get down to this stuff, which if you study physics at university, you will deal with quantum mechanics and quantum foam, string theory, and Planck length. Okay. Okay, extremely small. It's the stuff that makes up everything, basically. Okay. No, it's different kind of string. Okay, it's a different kind of string, but it's 10 to the negative 35. Okay, so it's 0 point and then 34 zeros and then the 1. Okay, so obviously, and physicists would deal with these types of numbers. Okay, and you know, obviously, you don't want to be writing out 34 zeros each time. It's a lot quicker and easier to use this one. Okay, so if we go back. So that brings us back to the start.
There we go.
All right, so you can have a look at this as a scale of the universe. It's pretty nice to relate all this back. But for now, okay, we need to actually figure out how we go from numbers that we're used to into standard form, okay, or scientific notation. And I think we all probably have a good idea as it is. So, let's write this down. Every number in scientific notation must have a coefficient and a times 10 to the power of something. Okay, it's always made up of two parts. Okay, so it's always made up of two parts, the coefficient and the times 10 to the power of. Now the important thing is your coefficient, which is always the number at the start, the coefficient must be greater than or equal to 1, less than 10. Okay, so the number at the front must always be bigger than 1, but less than 10. Okay, that's really, really important. If it's not, then it's not in scientific notation. Okay, the first number has to be between 1 and 10. Okay, now actually putting numbers into scientific notation, dead easy. Okay, so we'll do the first one together to show you how we go from this into scientific notation. I'll wait till everyone's ready.
Yeah.
1, 2, 3, 4, 5, 6. Yeah. Alright, so we said our first number must be greater than 1 or less than 10. So looking at this, looking at what we've got here, what do you think our coefficient is going to be? If it has to be greater than or equal to 1 but less than 10. Yep, Nicholas? Alright, 4.98 seems like the sensible thing. Okay, so 4.98 is definitely less than 10. It's also greater than 1. We also said we have to have a times, we have to have a times 10. And we now need to work out what this power is going to be. How are we going to figure out what the power will be? Sander? Okay, now you would think. Okay, yeah, it's more to do with the decimal place. Javian? Yeah, you could do that actually, that would work. But if I had to say about, because we want to think about it with the decimal place. What do you think, Taylor? Alright, so it'll be the same as the previous one? Okay, that's right. Okay, whereabouts is the decimal point in this number? We can't see it, but there is a decimal point. Whereabouts is it? Is it at the start? Is it... Where's it on? Yeah, it's right behind the last zero. So our decimal point is right here, okay? And where do I want to move it? In between the 4 and the 9. So I'm going to move it 1, 2, 3, 4, 5, 6, 7. I'm going to move it 8 places. So it would be like that, okay? So we're counting how many places we move the decimal point to go from where it is at the minute. 1, 2, 3, 4, 5, 6, 7, 8 to where we want it to go.
So from the first 0 to
yeah. Okay, so you try this one. Put this into scientific notation for me. Let's 310.
listen 3
So 310 billion. Let's put that into scientific notation. Alright, good, good, good. So what's the number at the front going to be? Hands. I've gone around, most of you have it, so let's get some hands. Thank you. Magnus.
3.1
Yep.
times 10 to the power of 11.
Alright, good, you've done the whole thing. Okay, now let's check the 11. I think you're right. So we were moving from here. It goes once, twice, 3, 4, 5, 6, 7, 8, 9, 10, 11. Good. Alright. So you have to make sure that you count accurately. You have to have the number in front must be bigger than 1, less than 10, and you have to have your times 10, okay? All good, Eden? You're going to ask a question? No? All right. We have got 5 minutes. Let's have a go at the... cheap.
I think one extra one. Oh, I guess this is fine.
Oh, cheers. Oh, yes. Yeah, the first one. And everyone's on the right track. We've got 625. Well, the number is going to have to be 6.25 because that's the only way it can be bigger than 1 but less than 10. And then multiply by 10 to the power of. Yeah. And the good thing is you can check it by putting it in